The first time ever I forgot my notes, so I'm going to read them off my cell phone, so things may look a little bit funny today, but I'll give it a go. Unless anyone printed them. Hey, that was always a long shot. Okay, so I haven't seen you guys for a while, so let's just recap before we begin. So to recap, this is called a series or a sum. We can take the sum of this series, which means that we're going to add up these individual summings. And we know that these series, so this series, can converge or diverge. Right, so at the moment we're just concerned about calculating if these sums will equal something finite or if they'll go off and sum to infinity or negative infinity. So what sums do we know about? So let's just go through what we know. So we have the sum of 1 over n from n equals 1 to infinity. What is this?
0.
This is 0? How's that possible? The first thing I'm adding is 1. This stresses me. Okay, so this is the harmonic series. And is it divergent or convergent? That is, does this sum to infinity or does this sum to something that's not infinity? Okay, divergent. So this is our go-to example for a divergent series. Next, what about this guy? What is this? Try again. What? P series. This is a P series. This is gonna drive me nuts. I may have to switch from saying series to sum, or this will go off every 9 seconds. Okay, so what is this? This sum is the P series, and is it convergent or divergent? It depends, right? Because if I set P equals to 1, it's the harmonic series and it diverges. So this is convergent if and only if, so only when P is greater than 1 strictly. Right? And it's obviously strict because if it's, you can't make it equal, otherwise you get this one. So what's the last series that we know of? So you said it was geometric, but can you tell me what the form is?
AR to the n minus 1.
What's a geometric series? Well, okay, it's this. R to the power of n, something to the power of n. And this is what? Convergent or divergent? So it's equal to 1 over 1 minus r, only when the absolute value of r is less than 1. Right, and since we have a closed form for it, that also means that it's convergent, obviously, because this is not going to be, I can't put infinity into that r. We also have the integral test.
If r is bigger than 1, it's divergent, right?
Well, you tell me.
Yes.
Yeah, of course, it has to be, because you'd have like 2 plus 4 plus 8. No, 2 plus 4. Yeah, 8, 16. The integral test, I'm just going to write it very, it's not nearly enough, but it's essentially this. This integral and this sum converge and diverge together. By which I mean, if this diverges, then this diverges. And if this converges, then this converges. And all of the other pairings of that. So the relevant thing here is that you have a function which basically passes through all the points of your series. I think this is a little bit easier to understand in my opinion. And then finally we have the limit comparison test, which has this setup. You have a bunch of series, all of which are bigger than 0. And if this is true, that's an, that's n. So you tell me what, if I know that this is convergent, what else can I conclude? If I sum these and we converge. Yes, then an is convergent. Okay? And if I know that dn is divergent, what does this tell me about an? Divergent, right? Because it's the thing in the middle. So if this goes to infinity, if the sum of this goes to infinity, then the sum of that has to go to infinity. If the sum of this becomes finite and this is smaller, then the sum of this has to be finite. Okay, so that's basically a recap of everything we learned about series. I probably should have written this on that board, but then YouTube would have been screwed. Okay, so today we're going to talk about something different. What have you noticed about the sums that we've been dealing with? Anything in particular? Have you noticed that our series and sums have never included negative numbers, or usually don't include negative numbers? Like nothing I've written on the board up there had negatives in them. Right, so we've sort of been hiding this away. Now we're going to talk about what happens when we have series like this. So suppose I got the sum of 1 over the n squared, but this is times minus 1 to the, let me see, k plus n plus 1. So n goes from 1 to infinity. This is going to be something like 1 minus a quarter plus a ninth minus a 16th plus a 25th, and so on. Now, does this converge or diverge is going to be the question now. And this is going to be more tough, right? Because it's like we have two series. We have a negative series and a positive series. So at the moment, let's just focus about what we can do with this example. Now, do you think this is convergent or divergent? Okay, so this sum is very close to this sum. Right? Just this without the negative. Okay? Is this convergent or divergent?
Convergent.
Why?
P series.
With
the n bigger than 1.
nope.
The p.
P greater than 1. Okay, so this is a convergent P series. Okay, but notice that this has to be bigger than the sum of n equals to 1 to infinity of 1 over n squared with the alternating term. Right, it has to be bigger. I'm taking every negative here and making it positive. Right, so this can only make it bigger. I can also bound it from the left-hand side by the negative version of this. But the point is, something with negatives in it, one of two things are going to happen. Right? If this is divergent, either the positives have to sum to infinity to diverge, or the negatives have to sum to infinity to diverge. Right? One of those two things have to become infinity. We'll talk later about what happens when you add enough and then remove enough. That's another situation. But what can we deduce if we know that the sum of this is convergent? Well, I'm going to write it out for you. So first I'll give you a definition. So what I'm going to say essentially is, if we look at a sum with an alternating series, and we just remove all the negatives and make them positive, if that series is convergent, then the original one was also convergent, because it has to be smaller, right, and not negative infinity. Otherwise, that negative infinity would have appeared in the absolute version of the sum. Okay, so we have this notion of absolute convergence. And absolute convergence is, so given this series, this absolutely converges when the absolute value of this converges. Right, so we have this notion of convergence and absolute convergence. Okay, so let's test our understanding here. Is this convergent? Is it absolutely convergent? Yeah, trivially. Anything that's convergent is also absolutely convergent. No, wait, that may be wrong. Well, okay, so I'll give you the precise theorem. I got to be careful because tomorrow we're going to be discussing alternating series where things can get a little bit more fishy. But we have this theorem. If we know that sum of A of n converges, this means that sum of AN converges. Okay, so if you remove all the negatives and add it up, if that's convergent, it must be the case that this is convergent. Notice the opposite isn't true. So here's an exercise while I wipe down the board. So note, it is not the case that if this is convergent, it does not imply that this is convergent. So I want you to find a series so that, or find a sequence so that this diverges and this converges. I don't think you can answer this yet, but think about it. Okay? You may need alternating series in order to get that. So that's basically all you need to know from today. I'm going to teach you a couple of their tests. But essentially, a lot of the time when I give you an alternating series, you're just going to be applying the same old techniques you have and just removing all of the negatives. This will become much more obvious in examples.
Would it converge?
What converges?
So 1 over n times negative 1 to the power plus 1.
Can you prove that that's convergent? Because that's called the alternating harmonic series.
Yeah, the original one diverges.
Yeah. So you're saying the alternating one converges?
Yeah.
You're right, but I can't show you why until tomorrow. You can't answer that question at the moment. I want you to think about it. That's sort of a motivating question for tomorrow's lecture. Because the answer is the harmonic series and the alternating harmonic series. It turns out the harmonic series diverges, but if you alternate the terms, if you go 1 minus a half plus a third minus a quarter, that actually converges. But we'll learn why tomorrow. Okay, so here's our first example, just to show you that what we're doing today isn't altogether that new or complicated. If I give you something like this. Oh, okay, so I just did an example up there. I'll do a different one. So there's more in the notes, but I think I may have duplicated it. So let's just consider this guy from n equals 1 to infinity. So is this convergent or divergent? Right, if you saw this on your Weeby work, how would you approach it? That sign really messes with us. Okay, so what's one of the problems with this term up here? Well, it's positive and it's negative, it's positive, it's a negative. Right, it's sometimes positive and sometimes negative. It's not even as nice as that series, because that series has an alternating sum. This has a sum where some of the negatives are occasionally negative and some of them are occasionally positive. Right, so naturally this looks like it's something complicated. But if we can show that this converges, then we can show that the original thing converges. Okay, so we can throw some absolute brackets on here and think about it. So can you tell me if this converges or not? How?
Because that's basically a 1.
Okay, yes, that's the right way of thinking about it, but how do we codify that? I wrote down everything we knew about series at the beginning of class. Right, that's the entire tool set at the moment.
It's the p series multiplied by sine of n, and then we could say that sine of n just half is positive, half is negative.
Okay, you're all going in the right direction. What you need to apply is the limit comparison test. Right, because we know if this is an, so suppose an is sine n over n squared. The absolute value of this is always less than or equal to 1 over n squared. Right? The biggest sign can be is 1.
And that
Right?
converges.
So this always has to be less than these individual sum-ins. Each of them are less than this. Right? So actually, we have that this sum is less than or equal to that sum. Right? And what is this sum?
P series and convergence.
P series with p greater than 1, which is convergent. Right? So this is a convergent P series. Right? So by the limit comparison test, we have that the sum of sine n over n squared converges, which means by that theorem, we have that the original sum converges. Okay? So you're always going to have to use these tools in concert with other tools. It's unlikely to be just one. Right? You usually have to use the absolute convergence test. I'm going to show you the ratio and root test, but it's usually the case that you need to throw a limit comparison test in somehow. Because you usually need to produce a sum that's either convergent and divergent and compare with the thing, right? Because we're never going to give you something nice like this. We'll usually give you something weird like that, which is close to something nice. Okay, next test is the ratio test. I know I didn't do very many examples with this, but this is all the stuff that we did last week. I'm just saying, just throw absolute values on this. Forget the fact that it has any negative terms, and use all of the old tools, right? Because we know how to deal with series with all positive terms, right? So it's usually a test for absolute convergence, and using a limit comparison test. Okay, so here's a new test. So, okay, what time do we got? I want to know how much of this proof to do. Well, we got time. So in the ratio test, we are going to investigate the ratio of consecutive terms. So remember in the geometric series, so the geometric series was what? It's basically r to the power of n for r less than, the absolute value of r less than 1. So let's look at the ratio of two consecutive terms, right? So the nth term here is r to the power of n. This means that an plus 1 over an is rn plus 1 over rn, which is equal to r. And we know that the geometric sum converges when r is strictly less than 1. Right, so if this r is strictly less than 1, this implies convergence. Okay? For the geometric series at least. We are going to extend this result. This is the specific result. We're going to generalize this. Right? Because it turns out this is true for any series. Right? If the ratio of consecutive terms gives you something less than, strictly less than 1, you're going to converge. Right? So what was true for the geometric series, we can actually extend to all series. So here's something called the ratio test. This is an important one. This one works a lot. Right? This is one of the main tools in your toolkit. Okay, so this breaks into 3 pieces. So let this be a series. And then suppose that we look at the limit as n goes to infinity. And to make it simple, we're just going to throw absolute brackets on here. If we look at the limit of consecutive terms in the series, and we let this equal to rho, 1, if rho is less than 1, this means that the sum is convergent. if p is greater than 1, we have the sum is divergent. And if p is equal to 0, p is equal to 1, we have inconclusive. Okay? So basically we do a limit. So both of our tests today are going to break into 3 pieces essentially. Right? We're going to take a limit, and we're interested when that limit is in between 0 and 1. Right? We're going to get convergent behavior between 0 and 1 strict. We're going to get divergent behavior when p is greater than 1 strict. And we're going to get inconclusive information when this ratio is 1 precisely. So I'll show you some examples there. We're going to have to use a ton of factorials today. You're no longer allowed to not understand, because now they're going to be officially part of the curriculum. Is this board readable if I write on it? Okay. I don't know. Does anyone have any little bit of water? You have some water? Oh, look at that. Look at that. So much better. Okay, so let's do an example. Okay, so first just recall, I had this piece of, oh great, now it's too wet. Okay, I'll just start over here. Recall, if I write this, x goes to y, I've exaggerated that arrow. This means the limit of n goes to infinity of x is equal to y. This is just a sort of simpler notation to say this is going to that. Oh, okay, so in the notes, I have a proof of this, but I'm going to skip it, because I think I want to focus on actually applying the tool rather than why the tool works. But if you're interested in why it works, take a look in the notes. Okay, so we're going to have to now use the factorial. So can anyone tell me what 3 factorial is? So it's 6, right? This is 3 times 2 times 1. In general, k factorial is equal to k times k minus 1 factorial. And 0 factorial is 1. It's weird. Like I suppose you've never seen a recursive definition like this, but that's how it's defined. Right, so for example, if you had 4 factorial, this would be 4 times 3 factorial, which is 4 times 3 times 2 factorial, and you get all the way to the bottom where you get 0 factorial. And that's why we made 0 factorial 1. Because if we made it 0, every factorial would be 0. And it wouldn't be that useful. Other things about the factorial that you have to be careful about. Where did I put it? This thing keeps moving around. There's a little nuance here, right? X, y factorial is not equal to x, y, all factorial. Is that obvious? Be careful about what the factorial is binding to, right? This is equal to x times y times y minus 1 times y minus 2, and so on. This one is equal to xy times xy minus 1 times xy minus 2, and so on. Right, so the factorial only binds to the thing to the left. Right, so be careful. This is a common mistake that's made. Right, and you'll really struggle in your proofs if you're applying the factorial wrong. Now, why am I showing you this? Well, because often it is the case that in series, especially in combinatorics and statistics, you're going to produce, oops, this is an example. Consider this sum, n equals 1 to infinity of 2n factorial over n factorial n factorial. I'm going to make one lap. I want you guys to compute the first 3 partial sums of this, just so you can work it out. One lap. You want more donuts? I'll make another lap with the donuts. There's no minuses. Anyone donuts? Anyone? Yeah. All chocolate next time, okay. Donuts. These are delicious. Yeah, they're temporary as well. Alright, left side next. Okay, what do we got? Let's just do the first 3. Oh, I'm all out of sorts today. Here it is. Okay, so the first one is what? N is equal to 1. So that's going to be 2 times 1 factorial. That's 2. Over 1 factorial, 1 factorial. That's 1. The next one's going to be 2 times 2 factorial. 2 factorial is 2. 2 times 2 is 4. Over 2 factorial, that's 2 times 2, that's 4. The next one's going to be 2 times 3 factorial. 3 factorial is 6 times 2 is 12. Over 3 factorial, 6 times 6, that's 36, and so on. That's not really too important. I just wanted to make sure you can use the factorial notation properly. Now, the real question is this convergent or divergent? And like, this isn't a contrived example. Stuff with factorial show up all the time in statistics, probability, and when we'll see Taylor series. Right? Whenever you take successive derivatives of a polynomial, the things that fall in front of the terms are factorials. Right? X cubed goes to 3x, goes to 3 times 2. X cubed goes to 3x squared, goes to 3 times 2 times x, goes to 3 times 2 times 1. Right? You're producing factorials when we're taking derivatives. So just to convince you that this is going to be something that we'll need. But would you know if this is divergent or convergent or not? And notice, I'm not even asking you to find me an approximation for the sum, or indeed what the closed form is. We're basically, we've given up on that. Right? I'm only asking you if this is convergent or divergent. Right? So don't go looking for a sum. That's not the right way to do it. Right? You'll fail most of the time. Always answer the easiest question we're asking you. If I say find if this is convergent and divergent, sure. If you end up finding a closed form, great. But that was the hardest way to demonstrate it. You had a lot of other tools that demonstrated it, but less. Well, what tool do you think I use on this? Ratio test, right? So let's try the ratio test. So what does the ratio test say? It says that we have to look at the absolute value of the ratio of 2 terms. So I'm going to show you how to expand this. Oh, dear Lord. I figured I made a mistake here. Sorry about that. That's outside, which means all of these numerators are wrong. I'll correct them. So the first one is 2 factorial, that's 2. The next one is going to be 4 factorial. That's 24. The next one is going to be 6 factorial, which is already something bigger than I can do mental calculation on. But sorry about that. I could have continued, but I want to be consistent with the notes. Anyways, let's look at the ratio of 2 consecutive terms. What's the nth term? Hopefully, I assume that you can tell me what the nth term of this is. It's just this, right? So maybe it's a good habit to say this means that an is 2n factorial over n factorial n factorial. So if you look at the ratio here, what are we going to get? We have to be careful with how we expand this. We're going to get 2 n plus. I have to be really careful because now I feel like this isn't going to work out. What did I screw up? Damn it! You guys have to be nice to me. It's my birthday. I was right the first time around. This was 2n factorial. Yeah. So this means the nth term is 2n factorial over n factorial n factorial. So what are the 2 consecutive terms? We're going to have 2 n plus 1 factorial over n plus 1 factorial, n plus 1 factorial, multiplied by the reciprocal of this. Don't do a division. You're just going to waste time. Multiply by the reciprocal immediately. It's going to be n factorial over 2n factorial. Now, we have to simplify this. I don't want you to be wasting a ton of time, so I'm going to do a full expansion once, but we have to strive to not write it like this, right? Because it's going to be a waste of time. So, I gave you the rule for expanding factorials. It's this. So, what can I replace these factorials with? This is 2 times n plus 1 times n factorial. The bottom is going to be the same thing. N plus 1 n factorial, n plus 1 n factorial. The top was what? N factorial over 2n factorial. So what do we get? What can we cancel now? 2, n factorial, n factorial, n factorial, n factorial. These two, this one, and that one. In the end, we're left with 1 over n plus 1. What's the limit of this?
0 as n goes to
So, as n goes to infinity, this is equal to 0, which is less than 1. So what does the ratio test tell us about that sum? It implies is convergent. You're going to have to do this a lot in your exam. This is a very important test. I want you to get acquainted with it. We'll do more examples. Okay, let's talk about the, I'm just going to erase this board. Let's talk about the third case here. Can you find me a case of 2 series whose ratios of terms go to 1, where one diverges and the other one converges? Right? Give me a real example to prove to me that the P equals 1 case is inconclusive. Think about it. And you only have like a handful of examples to choose from. So don't think these are complicated. Remember, you only have geometric, harmonic, and P. Right, so think about it. So what's your go-to example for a divergent harmonic series? Happy birthday.
Appreciate it.
Yeah. What's your go-to example for a harmonic divergent series? Oh, Jesus Murphy. What is your go-to example of a divergent series?
Harmonic.
Harmonic, right? So conduct this test on the harmonic series and see what you get. Okay, here's an example. So let's consider this, the harmonic series. So 1 over n from n equals 1 to infinity. What's the ratio here? So the ratio is going to be given by the limit of n goes to infinity of 1 over n plus 1 times n over 1. Right? That's me dividing. Right? This is an plus 1 over an. I'm skipping some steps. It's filled in the notes. But what is this limit? 1. Okay. And is this convergent or divergent?
Well, if it's
Yeah, I'm trying to pound this into your head that this is divergent, right? That this is divergent. This is the divergent harmonic series, divergent harmonic series, divergent harmonic series. It is your most basic example of a divergent series. You're going to have to use it all the time. Right, so this diverges. Its ratio of limits, its ratio of terms in the limit is 1. What about this one? What is this? Why?
P series where P is bigger.
Okay, so this is P series, P greater than 1, right? So convergent. What's the ratio of its consecutive terms? Okay, so we're going to have 1 over n plus 1 squared times n squared over 1. What's this limit? Also 1. Okay, so here's an example of two series whose ratios go to 1 in the limit. And one is divergent and the other one is convergent. Thereby, if the limit of consecutive terms goes to 1, you can't conclude anything. This is enough to say, look, here's an example of something that's convergent and something that's divergent that has this property. So if it's 1, nothing can be concluded. Right, that's always going to be the boundary point. Next test. I have a lot more examples that I've stacked towards the end of class, just so I can get all the tests out, and then we'll do as many examples as we can with the remaining time. This is called the root test. This is where all my Australian students would giggle, because this is actually a naughty word in Australia, believe it or not. You look it up yourself. You guys aren't old enough yet. Maybe he is. Okay, so let this be a series as always for which you want to determine convergence or divergence. Suppose that we have the following conditions are met. The limit of n goes to infinity of the absolute value of an 1 over n, if this is equal to rho. I don't know why they chose rho. You can say p if you want. But again, notice that we're always looking at the absolute version of the summons. That's going to make things a lot easier if negatives aren't introduced. So we have 3 cases here. Can anyone guess the cases? What do you think the 3 cases are for this test? I heard it. Well, we're going to have what happens when p is greater than 1, what happens when p is less than 1, and what happens when p is 1. And so both of these test cases have the same categories. Okay, so if we do a root test, if we look at the nth root of the nth term, and that goes to something that is, I should list them in the same order. Less than 1, greater than 1. So if it's less than 1, we have that this is convergent, which means that an is convergent. If p is greater than 1, there's 2 cases here. Whoops. Oh. Okay, they list this as 2 cases, but I regard it as the same. That's why I don't bother writing it. So the book and the notes write, if p is greater than 1 or infinity. But it's like, well, that is greater than 1. But technically, it can go to negative infinity, right? So I guess in both cases, I have to specify p is greater than 1 or infinite, right? Either infinite. And here, is or infinite. But it's a detail that I don't even think is worth mentioning, because infinity is bigger than 1. Okay, so if it's bigger than 1 or infinite, then this is divergent. And if it's equal to 1, again, inconclusive. Right, so the easy thing to remember, I brought some donuts. Happy birthday. The categories in both tests are the same. Right, so it's going to be easy to remember. And don't memorize these two things as different. You just have to test the limit in both cases. Okay, I'm going to try to give you an example to do while I wipe down the boards. Murphy. Okay. Try this one. It's going to be a little bit tough, though. You're going to have to use a lot of your tools from earlier on in the class. So here's an nth term. It's given by n over 2n for n odd. 1 over 2n n even. And I want to know, does an converge? Give that a try using the ratio test. Using the root test. And I'm sorry I can't give you much like intuition or explanation or geometric explanations as I was during calculus, but these summing things is just weird, right? When you start talking about adding together an infinite amount of numbers, weird things happen. This is almost why mathematics had to be invented, to start dealing with these absurdities. Because you wouldn't expect that you could add an infinite amount of stuff and get a finite amount of stuff from that. At least I don't think that's very intuitive. All right, so what about that one? Anyone have any ideas? Well, you have to use the root test, right? So I'll show you. Maybe you're forgetting some of your old techniques. So what do we need here? If we're doing a root test, what limit do I need? Well, I need to calculate the limit of n goes to infinity of the absolute value of the nth term, nth root. Okay, so I need to somehow compute this limit. So the new question becomes, how do you compute this limit? Remember squeeze theorem? Rings a bell? Please review it, because that's what we're going to use now. All right, so obviously, an is trapped in between 1 over 2 to the power of n and n over 2 to the power of n. Everyone agree with this statement? And I can put the absolute brackets everywhere, but all of these terms are positive to begin with, so let's not include them. It just makes it more complicated. So everyone agrees with this? Yeah? So I can now use the squeeze theorem to conclude this. Oh, sorry. Okay, the next thing I want to do to this inequality is apply the nth root everywhere. What falls out of this? What's the nth root of 1?
1.
What's the nth root of 2 to the power of n?
2 to the 1.
So 2.
Yeah.
This is going to be less than or equal to an 1 over n. And then here we're going to have the nth root of n over the nth root of 2 to the power of n, which is 2. Everyone follow? Okay, where do we go from here? Now, I just apply the limit everywhere. 1/2 is less than the limit n goes to infinity. Infinity of an 1 over n is less than or equal to the limit of n goes to infinity of the nth root of n over 2. This is going to be by squeeze theorem. Okay, what's the limit of n goes to infinity of 1/2? Half. This is the thing that we're looking for. So I'm just going to write it in again. And what's the limit of this? Let's break it up into 2 pieces. The denominator is 2. So what's the limit of 2 as n goes to infinity? 2. Okay. So I'll give you the bottom. What about the top? You can, but you should just remember this one. There's some of them that you should just know. So remember, the nth root of n goes to 1. That's one of the identities you had from earlier on. Just write them down on a piece of paper, or check that. I think we even put them on the your final. Final submitted, by the way, and approved. Yeah, sad face. Okay, so what did we determine the limit of this guy is then? Yeah, so I guess this is really where I'm applying squeeze theorem, but we get the limit of n goes to infinity of an to the 1 over n is 1/2, which implies what about the sum?
Convergence.
By? Convergent by root test. Right? Because 1/2 is strictly less than 1. All right, so we fall into category 1 of the root test. Okay, so I'm going to give you another one. You guys try it now. Maybe it'll be a tad easier. So here's an exercise. And I'm pretty sure that's all the tests I needed to teach you today. Okay, so those are all the tests. Right, so you learned about, so to summarize what we learned today, you learned that a sum can be absolutely convergent. That is, if you have a sum with some arbitrary and negative terms in it, you can drop all the negative terms. Well, you can drop all the negatives and add them instead. And if that series converges, that series being called the absolute version of the original sum, then the sum is called absolutely convergent. And any sum that's absolutely convergent is also convergent. Right, so that means you can use your tools on a sum with only positive terms, which is great because I've only taught you tools to use for sums which only have positive terms. The second and third thing we learned today is this root test and this ratio test, which you can use to conclude about the divergence or convergence of series by looking either at the limit of the ratio of consecutive terms or the limit of the nth root of the nth term. And in both cases, we make a decision based upon whether that limit is less than 1 strictly, greater than 1 strictly, and we can't conclude anything if it's equal to 1. But that's comprehensively what I was going to teach you today. The rest of the class is going to be us trying to do exercises. How much time do we got left? An hour. Perfect. Okay, so maybe I'll actually give you time to work on these a bit. So why don't you try this one? 1 minus 3n over 2n plus 1 to the half. to the n. Is this convergent or divergent? Give that one a try. I'm going to write a bunch more on the board. Okay, so I have 1, 2, 3. I have 3 questions left, including this one. So I'm going to let you work for 10 minutes, and then I'll take it up. Then I'll give you a new question. You'll work on it for 10 minutes, and we'll take it up. And I'll give you another question. We'll work on it for 10 minutes, and we'll take it up. That means you have a half hour of individual work. So start working on this one. You know what? Just to make it...